Hello, everyone, and welcome to the first proper episode of the AGI show, where we talk about the future of artificial general intelligence, its timelines, its implications for the world, any challenges it poses for humanity as a whole, and how we go about making sure that we account for those risks and challenges, and ensure that ultimately AGI is has the most positive impact it can on our world and our planet. You'll see in this first episode in just a minute that we actually have two hosts. We have myself and we have my good friend Hunter J. So Hunter and I actually started this podcast together, and he's still going to be quite involved as an advisor and as a guest host and a guest appearance on many episodes. But one thing we decided together after recording this first episode is that having two hosts wasn't quite the best interview experience or the best listening experience for our podcast listeners. We accidentally, talk over each other and things like that. The challenges we've all faced if you've ever used Zoom or had a long video call. So after this first episode, it'll just be me on most episodes as host and Hunter coming back as advisor or as a guest host on many topics. But after we recorded this great interview with an alignment researcher named Logan, we had far too many interesting conversations about the future of artificial general intelligence, the timelines, the possibilities, the risks, not to share this with the world. So with this brief intro as to why we've got two hosts on this particular one, I want you to take away all the great learnings that we did out of this session with Logan, who was an incredibly knowledgeable and capable expert on the topic of artificial general intelligence. So without any further ado, I'll let you jump into this interview with my co-host Hunter, myself, and our great guest Logan Smith. I hope you enjoy it.
What happens when humanity creates machines that are more intelligent than we are? Machines that can do everything a person can do. Machines that can self-improve, that can pursue goals, that can outcompete us. In this series on AGI timelines, we'll be taking a look at how these machines might be built and when that might happen. In later episodes, we'll dig into the implications of AGI and how we can work to ensure that they benefit humanity's goals. This is the AGI show with Hunter and Soroush. My name is Hunter J. I am the CEO and co-founder of a startup which is doing automated fruit picking, and I've been a software engineer for the last 5 years.
My name is Soroush and I'm your co-host. I've worked in software and technology for my entire career, spanning over 10 years, with stints at Plaid as a software engineer and engineering manager, and now as a technologist over at a company called Vow. We make cell-cultured meat to give us meat options without the environmental and ethical negative impacts. And today I'm really, really excited to speak with Logan about all things AGI and its implications.
Our guest today is Logan Riggs Smith. He is an independent AI alignment researcher funded by the Long-Term Future Fund and currently works with large language models. Thanks for jumping on the show, Logan.
Yeah, thanks for having me.
So to start off, what is alignment research and how did you get into it? Why did you get into it?
Alignment research is how to make artificial general intelligence safe when it becomes available. And how I initially got into it was actually, realizing 150,000 people die every day. We can prevent this with AGI, who can do all our research for us and cure all the diseases. So I was trying to make a presentation to my university on why we should build the AGI now to, cure all the diseases and so on. And then during my research on the presentation, I realized that an AGI actually might have different goals than us, and that could end up having catastrophic impact. And my thinking now is that, I think it's like a 10% chance. It's pretty low that it's actually going to do these bad things. But a 10% chance that like I die going home tonight, I like through the car and Uber, like I would rather walk. A 10% chance is really high. So I work on the safety part, which seems more neglected than the improving capabilities.
And
Okay, well, let's
and
start at
Hunter,
the.
just
Sorry, go on,
just
Soroush.
no, just because we're gonna have audience members who are all different places in their kind of journey into learning about AGI, I just want to make sure we're all talking about the same thing. Logan, do you want to just briefly say when you use the word AGI, what does that mean? Well, let me tell us what it stands for, but then quickly tell us what does that mean to you? What's your definition in this conversation?
But yeah, AGI is artificial general intelligence. Uh, it doesn't have to be like human level intelligence, but it could maybe act intelligently in a wide uh, distribution of environments. I don't know, maybe solving math or doing art. But it's like the same model doing all the same things. Maybe at human level quality. For example, like research would be a pretty transformative task that it could do.
Thank you.
So, why do you think this sort of thing is possible in the first place? Why do you think we would be able to build a machine that's intelligent?
There's several different arguments here. Like one is like, do you believe human level intelligence is some like special value that machines will never get to? And that just doesn't seem very like a very likely argument to me. Uh, as far as like, maybe humans are Turing complete. We can like run any program or whatever, and things that are Turing complete can also run other similar programs. Uh, just as a very general argument. And another one is that we seem very inefficient as far as like processing. Like our neurons don't process as much as um, silicon.
They like fire and they only travel at 200 or 300 meters a second versus the physical limits of how fast you could send that information. Is that the sort of thing you mean?
Yeah. But I think the thing that I would expect most people to disagree on is that this is going to happen anytime soon, like within your lifetime. Like maybe this is a few hundred years from now. But like I can see advancements coming out this like past 2 years that made me think like, yeah, this could happen like in this decade. Uh, in my view.
Just to set a
Okay,
little
well, let's
background.
dive into that.
Oh, sorry, Hunter. Just to
Go through.
just to set a little bit of background, just make sure we're kind of taking our audience members with us. Logan, you're imagining this thing is a machine intelligence, so it's running on silicon type systems. Is that right?
Yes.
Yeah, fantastic. And do you want to just give a little bit of a picture of what this thing could look like? Is it something running in our existing kind of understanding of computing? Just set a bit of precedent for some of the things you talked about in terms of how it might happen.
I can imagine like we have like language models now. I'm unsure like what you mean by like running what computation.
Do you imagine it, yeah, it's running on distributed computing? Do you imagine it's running on some sort of neural network? Sorry, not neural network, but like a biological approach.
Okay.
Just maybe a little bit of like what this looks like in your view.
Yes, our current paradigm is not like brain-based algorithms. It is very much just machine learning. And it does seem likely that we could get to AGI even using our current paradigm. But my viewpoint is that we could use our current paradigm to automate large portions of machine learning research. And then if like we can't build AGI with our current paradigm, our research accelerated could find some maybe neurological basis or some other paradigm that is able to actually reach AGI, even if our current paradigm cannot.
Really
like,
helpful.
So you're suggesting scaled up, improved neural networks as they exist today, going from, let's say, I don't know what they're at today, 200 billion parameters to a trillion parameters, say. Maybe that's hitting the limits of efficiency of data, that sort of stuff. but might be good enough that it could start accelerating its own, as doing its own research, or at least being a research assistant for further AI research. That's what you're kind of saying.
Correct. Although it still actually might.
It might just be able to
It
scale
might
all the way
be-
up. Yeah, yeah.
That's really
Because there have been some crazy breakthroughs recently. Well, not even breakthroughs, just scale increasing seems to open up a lot of different tasks for AI. You've been doing a lot of stuff with language models. Could you take us through the big shift there? Was a couple of years ago that what sort of made them suddenly become useful for copywriting and lots of other tasks?
Yeah, throughout, I guess maybe in like 2017, I'm going to get the specifics wrong. It's like GPT-2 came out, and this is a like next word predictor. So you give it a bunch of text, it predicts the next word, and you can do this repeatedly to make it generate like several paragraphs, because a paragraph is just word after word. And it was really, really bad. It could say some interesting things, but it was obviously AI generated. But then they scaled the model up maybe like 100 times, all the way to like 175 billion parameters for GPT-3. And they didn't do anything really fancy, maybe a small like architecture change, but it was basically just the same, but larger parameters and maybe some more data. And it just got way better on all the different metrics. And one interesting thing was that it was able to do, they were saying, like few shot prompting. Like you gave it some new task, and you gave like 2 examples in the prompt, and you got it to do next word prediction for the third question, and it could just answer it pretty well. And since then, people have done like scaling laws to see like as you just increase parameters, does it just get better and better? And recently, Chinchilla is the model and paper by Google. And they were showing that it's both parameters and data. Like, so as you scale parameter 2 times, you need to scale data 2 times to get
That's training data. The number of different examples it sees of text to do next word prediction.
Yes. Yeah. So like another, yeah.
And obviously it has to be real text. You can't just create a bunch of random words in an order. You're trying to encode useful information, so it has to be real text that's written by, well, so far it's been written by people. We'll maybe touch on auto-generated text later. Yeah, okay. Sorry, keep going.
Yeah, and they just showed it was like, you need some like 1 to 20 ratio of parameters. So if you have like 1 trillion parameters, you need 20 trillion tokens. And it was showing a lot of models that people were training inefficiently. They had way less data. Like if they had 1 trillion parameters, they would have less than 1 trillion data, which is way inefficient. But just for like some context, like how much data is 1 trillion? So it's about like 1 word per like data is what I'm how it's defined. And it's been sort of calculated that on the internet we only have like 1 to 3 trillion tokens or data points. And so we've already like kind of peaked with the models we've been able to create. And what is like a 70 billion parameter model already has like 1.4 trillion tokens. So it's like, we seem really bottleneck constrained or data constrained. Like Google came up with a 500 billion parameter model, which like should require 10 trillion tokens. It's like 5 times as much as we have in the entire like internet. And there's like, it seems really data constrained.
So, Logan, just for our listeners at home, I think most of them will be, familiar with neural networks and some of the basics there. So I think data will be very clear. A word and a sentence, you can look at that and take some meaning out of it. You talk a lot about parameters and scaling parameters. What do parameters mean in the scale in the context of large language models, and how should people think about how hard or easy it is to scale up these parameters for these models?
The parameters are just more layers, like wider layers. in the model. So in this case, are transformers, and the layers are either like these attention head layers, or these like multi-layer perceptron layers. And as you scale up, it's actually interesting. The majority of the compute is the MLP layers and not the fancy attention one. Like even up to like 80% of the compute goes into that. So like that's really what it means as you scale up. Is you just attach more layers and more compute goes into the.
And so a good proxy for it in terms of resources would be compute. Obviously, that you wouldn't apply, different things take different amounts of compute, but you can largely correlate more computing power, or at least a better architecture for that computing, will be applied to create bigger parameter models.
Yeah. And the
inefficiency. There's three things going on here. There's the size of the model, the training time, and the amount of data. We've only spoken about two so far.
Yeah. So which one? The training time?
Yeah, that would also be related to compute, right?
Yeah. Yeah. I guess it's just like depends on how well you parallelize. Like if you have like a million GPUs, it'd take not very long at all. Yeah. The main constraint is compute, because you just like, hey, for a certain compute budget, we need this much parameters and this much data to like make the most use of it, or to be the most efficient use of it. As far as training time, I think normally they take like 40 days or whatever, but like it could take less if they had more GPUs and like better distributed computing software infrastructure.
The main constraint has been compute so far, but you're suggesting we're going to run into a data constraint as the models get bigger and we start using the data less efficiently. Can we overcome that by just training for even longer? Or actually, it sort of indicates that there's something here which is different about biological brains than these artificial neural networks, because we don't need to look at 3 trillion examples of word prediction to be able to generate really good word prediction. I mean, I suppose what I'm trying to dive into, there's a couple of possibilities for why that's the case. Do we have just biology has a much better intelligence architecture that we have a chance of discovering with neural networks? Or are we doing fake generation of text by thinking? Are we training ourselves by generating more examples ourselves and bootstrapping our way up? What do you think the future is for these neural networks? Which way do you think it'll go for improvements like that?
Yeah, one small point on the other one, which made me think there was a slight confusion, is like normal ML, you train for like multiple epochs, like you train over the data multiple times. But in these big models, they only train once. They only see each data point once, and everything else is just not as efficient or like causes problems, which was a real weird thing than compared to whatever I did in graduate. And then on to the second one. There's an interesting point. Like humans haven't seen this trillion tokens, but it's also like we have like multimodal data. And I think importantly, multimodal as in like we see vision and text, and we can hear things. And language models only see text, like one modality. And then there's also an important point that like we have agency and we can choose what examples we can come across. For example, I can choose to read a physics textbook. A language model cannot choose what it sees next. And in fact, its outputs do not affect the next thing it sees. Right? It just outputs the wrong word, it gets corrected, and then the next word in the book gets put in front of it. Doesn't matter if it does well or really bad, it's still going to see the next word in the book, and then the next word in the book, and the next word. Which is also an interesting point, because they're actually very safe, because they've never been trained to like take control of their input channels. Whereas for humans, like we very often choose what inputs we see. If you read a physics book or watch a certain video or listen to a podcast, these are all things you've like chosen to like to listen to or watch.
Yeah, we have so much agency. what we choose, what we even choose to learn. We can be like, oh, I don't like physics anymore. I'm going to move over to ballet because I'm better at that anyway.
We know you are, Soroush. Presumably, you could turn a large language model into an agent just by plugging its output into a normal computer and its input from the readout from the computer. Um, Although I suppose that naive approach wouldn't resolve the useful, like choosing useful training data for it problem. Um, are there domains where we can narrow in or generate, like let the model generate useful training data, or find
Yeah,
or choose its training data?
I can imagine some where you like access the internet and it can choose which things it can access. But I don't know. Like there's like something called WebGPT where they did hook it up to, I believe, I didn't actually read the paper. Shame on me. And they hooked it up to a small like database of like papers such that it could like when it's given a prompt, it can look up the database and see similar examples. Or maybe some other code does that for it. Uh, yeah, but I can imagine you just like have some metric, like score well on like answering questions, and you have access to all of Wikipedia, and you can like do search.
Mm,
Uh,
mm,
but, like even there, I don't think that's going to be a huge improvement at all
mm.
compared to just like training on all Wikipedia.
I did see an interesting one which was doing there was they were trying to use a large language model for programming, similar to something like Copilot, um, and they got a fairly decent performance gain by getting the model to generate its own programming questions and answers, which they put into the training set for the next generation. Um, and that worked pretty well because in normal circumstances, if you get it to say generate an essay, it's hard to automatically assess how good is the essay. Should we put that into the next use that as training data in the next generation? Should we use that as training data in the next generation? But with the programming tasks, they were able to just run them afterwards and see do the things run
Sorry.
properly.
I'm just gonna acknowledge what happened because it's just too funny, and I'm cracking up and can't mute myself too long. Well, this is our first ever podcast episode, and Hunter definitely just like bumped something across the table or something, and I just couldn't stop myself laughing. So that
Yeah,
was my.
yeah, that was terrible.
This is good. It is real, folks. Sorry, Hunter, you were saying.
I was saying with if you use large language models to generate programming examples, so test problems and solutions to them, you can then just run those test problems and solutions, uh, and then cut out all of the ones which don't run afterwards, and then the ones that do run, you can put into the training set for the next generation of training. And doing this does improve the performance of the model like quite a bit. And presumably you could scale it up with more and more difficult training problems as you go. Uh, I don't know. It's quite a concerning one because it is like if this turns out to be possible to scale all the way up with harder and harder problems, then you've got something which you can bootstrap to actual, uh, to do ML research itself. Um, yeah, I don't know. That's one that concerns me. Any comments on that from either of you guys?
Yeah, the so when I think we could, it seems quite likely, maybe 50%, we could automate machine learning research in the next 4 years, or this might by default happen. Only 50% chance. Maybe it happens like a couple years later.
Only 50% chance that we'll automate ML
And
research in
it
four
might be
years.
just good. It might be good to just quickly connect this back because we've obviously talked about a lot of topics, and I just want to kind of take us back just from the top. So, you know, we came in here talking about is artificial general intelligence possible, and if it is it soon? Is it a super long time from now? Do we have any of the relevant technologies now to get there, or are we close? So we talked about um, there's different pieces in training the models as we understand them today. the training time, the model size, and the data set size. And we talked about how data was a bottleneck for potentially making these models much, much more capable in terms of being something closer to what we would call an artificial general intelligence. And that's how we've now gotten to this challenge of, okay, well, how do we get more data if we've exhausted the internet? Yeah, Logan, it might be good for you to just speak a little bit to how you think we might solve that data problem. And it sounds like ML automation is related to that. Do you want to jump in from there?
Yeah, and to be clear, I don't want to solve that bottleneck. I want to make sure, figure out how it's safe. But like just predicting what people are already going to do.
Yeah.
Because as Hunter mentioned, like there is already a paper on, hey, we just generate data like this. The language model can generate more data. And like coding is a interesting domain because you have metrics that are like, I guess, automated already, like code correctness. And then there's other things that are pretty close, like generating unit test. Right? This function should do this, and the unit test will pass. And so one part of ML research is writing up experiments. And as far as like automating code for a large extent, I think this will happen more and more. Like for Copilot, which is a code generation thing from Microsoft or from GitHub, I guess, which is owned by Microsoft. Like people at Google, like 3% of their code, like recently was Copilot.
Oh, we use it at work at Val, and I'm less on the coding side than I used to be because I'm just more across kind of the management layers. But in terms of watching people code, it's completely changed, and a lot of our people use Copilot to do a lot of coding. It's been a big dramatic change in coding in a short amount of time.
Yeah, it's mostly like so Copilot sucks when it's like new novel things, but if it's something it's seen a lot, it's really good. Yeah, and all those things seem correctable. Like one problem is like it doesn't really know the context of your code, like all of it. It could probably read in, but it still like just misunderstands what you were trying to do. And these things seem correctable if you had like there is already a lot of money going into it. So things like automating like data generation, like beyond just like taking data from people using Copilot, like automating unit test generation. For example, I can imagine I specify a description and the language model specifies lots of unit tests, which it can already do with Copilot. But maybe some things unit tests are bad or they misunderstand your description. But if you had a few people and you just hired them 40 hours a week to like go from like description of like functions to like unit tests of them and like selecting the best one or giving feedback on the like natural language feedback on the unit test that came, like you could create a large data set more and more. And like as you retrain it, then it's able to generate, maybe it was like only 1 out of 4 unit tests were good. But then now it's 1 out of 3 and 1 out of 2. And that like speeds up production. And as you do it, you also like figure out ways to like do it better or like tools that help you assist it. This is something that happened at Tesla. They actually do just hire people full time to do data collection, and they created tools to help them label like images of streets. And so in the same way you could do that with unit tests, and in the same way you could do it from like a description to like in like a code outline of like these functions should call these. Same way you could do that to if it fails a unit test that was generated from an outline or a description of the code, of like running through the code and like auto correcting, right? You can make the model create a program and then run through it again and like say, hey, this was wrong in my code that I just generated, and then get it to correct it. So you just run it through 3 times and it like creates better code.
And Logan, maybe it's a good thing to kind of take the implication there a little bit. What do you think? Okay, so we've got machine learning, large language models and similar models that are getting better. They now have this ability to would you consider this the category of synthetic data? Is this fair to call this the kind of the approach of synthetic data?
I don't know. Like it's not
Yeah.
pure synthetic data.
Sure, it's a mix of
Yeah.
automation and synthetic data, and so they use these things to grow the size of the data set they can play with, that they can learn off. What do you think are the implications? How good could these models potentially get in your view?
So it's just on the task of coding. So you're not going to generate another trillion words of coding data set through this method.
Yeah.
And the scaling law was like, you need another trillion tokens, and that's going to help like general knowledge or whatever. But like, if you just want to really go hard into like improving coding, then this will help. And if like when I think of machine learning, it's like writing papers and like writing code, and that's it's like yeah, that's like mostly it.
You don't necessarily need an understanding of physics or society or economics to do ML research.
Yeah, correct. You can ignore all that.
And again, what do you think is the implication of that? I think let's just take it the logical
Yes.
next steps. Yeah.
It would be maybe people who are like researchers at top labs who are actually pushing the frontier, or academic institutes. Instead of like running like one experiment every like few months, or like a set of experiments for one paper, like you could just run like 10 experiments in like a week, because like you can write the code very, very quickly. And this also lowers the threshold on the like quality of ideas to try. I don't know, so you can try a wide range of ideas. Although like I might go back and say maybe institutes like, I don't know, maybe MIT or Harvard might not be able to do it, because you have to have like a huge model, and the model is either I think it's just going to be local. Like people at Google, they're not sharing their large models, right? And also OpenAI, they're not sharing their large model weights. And even if they did, these are like hundreds of billions parameters models, and like you need a large, like a lot of GPUs and some distributed computing nonsense, which is quite a headache to like even run and implement. And so I do expect only big labs to have access to these models to actually run, and other people are going to have access to it through these through these top labs. It's like OpenAI at the moment has an API you can call, and so you can communicate with a model. So something like that would need to happen. But if these like models are like super, super good, that might not happen. It might be like OpenAI and Microsoft's GitHub Copilot, because they're connected. I think Microsoft gave OpenAI like loads of money for that.
So we have a handful of organizations around the world who could take these newer approaches around ML automation to accelerate their ML research, which in your view gets us, it's going to get us faster to this world of AGI.
Yeah.
How far does it get us? We're talking so far here about we have large language models which are trained on giant transformers with billions of parameters, and then we're adjusting the data going into them, or adjusting small things about the way the layers are connected together, or sort of small changes on large base models is kind of the stuff you're talking about here. Improvements to training and fine tuning, better synthetic data, stuff like that. How far do you think that this immediate naive approach could get us? Could we be generating new architectures for neural networks, something to the scale of the shift from RNNs to transformers, say? Is something like that required for hitting AGI? And how far could we get with the current approaches, even with these speed up of tests that we're talking about? Speed up of ideas.
Yeah, my thinking is not it's not typically AGI, but it's like, when do we automate ML? And the AGI is around that mark, maybe slightly before or maybe after. And I can go more into that later. But just talking about Just talking about the
Clarify,
ML.
what do you mean by automate ML?
Oh, ML research.
Like, yeah, wait. So this is just what we've been talking about with uh, using a model to generate like more synthetic data or ideas for how to plug in the layers together, or where like how long to fine tune on different attention to different things. That's the sort of stuff we're talking about.
Yeah, just like whatever Google's doing now to like release papers and build
Mm.
models. It's just language model can like make them do that 10 times faster. And eventually, like most of the work is being done by the language model.
Mm, mm. But how far does that get us without any big fundamental shift or big new
Uh,
ideas on how to generate intelligence?
yeah, this is unclear. I feel like it's partially an empirical claim to say like how much just like large, like huge amounts of data collection on a specific task, like coding or idea generation or writing like papers, uh, get you. Uh, but like the thing with this is that if you are doing, if maybe in like 2 years, someone releases a paper on auto-generated data from language models or like human in the loop that's like actually very successful.
Mm.
Then like in the next year, like a couple rounds of papers being released from everyone saying like, oh, you could do it this way better, or like we applied it to this task, and people actually taking this seriously enough to spend like millions of dollars on actual data collection uh, for like over a few months period. Um, Even with like our current models, I think this could accelerate people's research. Like my ability to do research as a Google researcher, maybe 5 times like as much. Like I could just run way more experiments or like come up with ideas I never would have come up with because language models so much better at like reading all the papers than me.
Mm.
Um,
Oh, so the language model itself is suggesting ideas, yeah.
yeah, that's one possibility. And there's like other task research. Like research is actually hugely multifaceted and like even just ML research. And so like you're gonna run
Mm.
into so many bugs. Like 5 times you're whatever, you're still gonna run into these weird bugs of like I told it to do this and it did something slightly different, which is pretty much the alignment problem, but on higher stakes or
Mm.
not as high stakes.
And Logan,
Uh,
correct me if I'm wrong, but the labeling side of that, that's not new, right? I mean, people have been using labeled data sets for a very long time for all kinds of problems, whether it be, self-driving, character recognition, all kinds of things. We've been using labeled data sets. So that part is not so new. But you're thinking we could combine that with some ability to generate or make better use of that data. Is that correct?
yeah, like in this case, it's not just human generating data, but it's like the AI generates data and then human says, "Oh yeah, this one's good," or
I see. I see.
rewrite this one but include this detail. In the
Right.
language
So more
model,
like human assisted, almost like if the AI is the writer and the human is the editor of sorts. Or
yeah,
Yeah.
yeah, yeah. So
yeah.
maybe one in n it checks and that uses that information. Yeah. So it's some sort of amplification of the human in the loop.
Mm. And as it improves, n gets smaller, so a human has to
Yes.
check fewer bad examples for every good one. Yeah. And you said this, you expect this to happen around the same time as sort of early week AGI? Could you take us through
Yeah,
that thinking?
yeah. There's like in my mind, if you automate ML research like near entirely, like I don't know, 90%, you can run I don't know 10 experiments a day as Google, where normally it takes like a month to like have an actual full paper if you're really trying. That's extreme. Uh,
Mm.
and you could
Mm.
find some like oh, this math topic and this ML thing was actually helps sample efficiency or data or compute efficiency, and you build this architecture, or you just like run experiments on architecture design, or there is a field of
Mm.
like
Mm.
architecture search, and I don't think it's very good right now. Like I don't think they came up with transformers, but maybe you can extend that by automating ML research and find an
Mm.
architecture
Mm.
that's much more sample efficient. And because you've been doing this data collection, that data that you've been collecting can be reused on this new, more sample efficient model. and maybe that does get you AGI, or maybe the next iteration, because once you have that better model, it can generate more data at higher quality and with less human input required.
Because there's a couple inputs in here, right?
Sorry,
there's like the amount, there's like the amount of compute that we have. So if we had very sample inefficient models, like modern day transformers are more sample efficient than RNNs, but they're still not very good. If we had 500 times as much compute or thousands and thousands of times as much compute, we could just make them really, really big, assuming we solve the data generation problem. But then what you're talking about here is, okay, not waiting for the hardware to get to that point. We could do it faster than that if we're generating different architectures that are more sample efficient, and then using that to bootstrap the generation of an even more sample efficient architecture. And I suppose there could be a lot of sort of low hanging fruit here, because we haven't tried many different kinds of architectures yet. It's very, very expensive right now to develop a new architecture and try it on a large model. We can try it with small models, but things that work for very small models maybe don't transfer very well to extremely large ones. So I guess yeah, there could be a lot of low hanging fruit here with lots of different architectures that haven't been tried yet, or that with a small insight, a small tweak, could massively improve it. And we do see that sort of change all the time, don't we?
Yeah, and it could just be a very simple architecture change. Like it would be transformers, but like one or two things are different. And it's like, oh, okay.
And
now we're off.
Well, yeah, and I wonder if, so certainly, I mean, I'm certainly one of the people that believes that these kinds of things are possible. That large language models combined with more data, and potentially tweaks could get us to some particularly capable agents. I think GPT-3 has been really amazing to see versus GPT-2, and it sounds like a lot more could happen. I do think somebody listening on this podcast is definitely going to be thinking to themselves, yeah, but large language models just won't be able to get there even with all the data. Logan, I'm curious of your take as someone who spends a lot of time with large language models. What are your thoughts on the ceiling for this type of architecture? Maybe assume a few tweaks can be made, but for those out there who might be thinking, actually, that's just not realistic. You can add all the data in the world, but large language models will never be a generally capable agent. What are your thoughts on that criticism or question?
Yeah, I was just actually about to go into like, I'm just saying this stuff, but there's lots of holes you can poke here, and it might be good to do that for the skeptical viewer. Current capabilities in language models are hard to judge because when you read the papers on largest models, for example, like Palm, which is like 540 billion model or parameters, you're not like, I don't have access to them, and I can't like run them on code outlines, or etc. I can't do that. They run it on like a bunch of other tests, like some math problems or some like logic questions.
Yeah, hard to see how much they've trained to the test kind of stuff.
Yeah, so it is hard to tell. Like if I was just going to automate code and ignoring the other complex stuff of part of ML research, it's hard for me to judge.
Yeah, fair enough. And in some ways, I always wonder how much of this is just an empirical question, right? How will we know the ceiling until we get there? Maybe there are some theoretical models we can come up for this, but how good can they get in terms of predicting that ceiling?
Yeah, and at the moment there is no ceiling in like scaling laws, unless a new paper came out and I missed it.
Yeah.
But like just the general argument of like training on more diverse examples of code generation, like makes it better at code generation, just seems like common sense. Like, yes, of course it'll do that.
And,
it's just
and do you think that will produce a general intelligence? Because I think it's easy for many of us, including our audience, to probably imagine that turning into a very good coding, tool, like something that you say, please give me, an app that does this and this and that, and potentially giving you a really high quality app. That would be obviously really capable and far ahead of the capabilities of today. Do you imagine those kinds of approaches could give us something more general than that potentially.
Yeah, and the way is it's not just like it gets better at code and now it's AGI. It gets way better at code, and this can get you to run your experiments like twice as fast, and then way better at and then ML research itself will produce the more sample efficient architectures or different training schemes, etc.
Yeah, and GPT-3 was an interesting one when it came out because it was in many ways general. It was stuck on one modality, but you can ask it about cooking, or you can ask it about coding, or you can ask it about, Darwin's travels, and it gives you some really clever answers. So it's not simply that this approach could give us a much better coding model. It could be that it helps us produce better architectures or more interesting data sets, which then produces GPT-4 or 5, these kind of more general models as well.
Like it's not directly scaling up to be general. It is doing the research to enable something to scale up to be general.
Right. There's like a two-step process there.
Let's touch on, you mentioned to me earlier about, we're talking about timelines for when we might hit AGI, and this ML thing seems like it could cause very short timelines. Some people have been talking about examining human brains as a sort of one data point for when we reach general intelligence. We'd expect the AI models to have some comparable degree of complexity or scale as a human brain does. I was just wondering what your take was on that approach of trying to work out when we'll reach AGI. Well, the models are still 100th or 1,000th the size of human brains. Therefore, we have that long until we'll reach something that's human scale.
Yeah, I mean, one thing is a lot of our brain is not useful for intelligence. Like it helps control your muscles and your lungs. But like as far as like reverse engineering the human like algorithm, and there's I guess two parts. One is like this seems hard, and two, it also the training data might be more important than the algorithm. And that's something to think about. I don't know. So for the first one, like reverse engineering, like C. elegans, like a type of worm, like very small amount of neurons, just failed. And people tried for like decades, and it's still just bad. No one can do it. And so it seems like difficult to like, we're probably going to reach some other way of getting AGI before we reverse engineer the human brain specifically. Now there are things, if I imagine we can automate ML and it's actually like very decent hot quality, like I can run like 10 experiments on my own that I can review. And so can like all the other 19 people on my team at Google. And we like direct our attention at like reverse engineering the brain algorithm. There might be way sample efficient ways of gaining that information, but maybe it requires building a very precise fMRI machine, or maybe you can only like, if you just get this information on the human, like learning in this way, you can reverse engineer that algorithm. I can imagine a lot of things, but like I am not a neuroscience. I don't even know whatever. This is all just dumb speculation. Lots of salt. And then the second part is the data part. Like humans, like we interact in environments, and as we mentioned earlier, you can choose to experience certain things. You can put on different metrics. Like in this metric, I'm going to try to win at this video game. And this other time, I have the metric of scoring well in my grade. In this other situation, I have this metric of like wanting to look cool in front of my friends. And you have all these like various metrics in different situations and ways of like learning from that and doing some transfer learning from other parts of your life. And so that might be something that really helps even like current transformers. Like maybe you just put them in like a special RL environment. And they're able to like learn a lot. Or maybe you have to figure out some stuff in transfer learning. There's like lots of different ideas, and some of them might take way longer to work out. Like they're probably going to work out, but like I don't know, like 50 years or something. If we just tried human brain emulation or something, versus I don't know, automating or like, I don't know, some clever statistical math combination with our current ML techniques. Um, yeah.
So you think that if we did it purely artificially, not just would we be able to develop the ideas faster than it would take us to dive into and understand human brains deeply, is saying we wouldn't even necessarily want to use the brain scale as an anchor for, okay, we need to get neural networks to this scale and complexity can before we think they'll have intelligence. As in, we've got very, very rough, like within 2 orders of magnitude guess of how much computation is going on in the brain. Uh, would that be a sensible thing to say, okay, this amount of computation is required for general intelligence?
I think it's so this is actually where the Cotra report comes in. I think the estimate is, and I might use the wrong prefix, but like the humans are running like 10 to the 16 flops per second. And this is on inference. Like right now, as we're talking, this doesn't include like how much it costs to like train a human to be this intelligent or whatever. So the equivalent with like GPT, it costs much less to just run it to produce a few paragraphs than to train it on all the data that made it whatever. It costs way less, like way more to train. And so as a human, the estimate from the Cotra report is like 10 to the 24 flops from the age of like 0 to 32.
Training flops.
Training a human, it took this many flops per second. So that's like 7 orders of magnitude more than or maybe 8 than the 10 to 16. Mm-hmm. But the thing is, we could run that now with just like $10 million. And I don't think that's true. I don't think we're at a point where we could just pay $10 million to scale up GPT and we have AGI. I think there's some parts that are missing, or maybe you just have to scale way harder. So Cotra actually like accounts for this and like adds like 2 orders of magnitude. Just because like we don't have AGI now,
why
so maybe
just add 2. Just add 2. That is plus 2 and we're good.
So now it costs $1 billion to make an AGI.
But the massive difference between inference and training is not something I'd thought about a lot before, about when trying to use bio anchors like this for working out timelines. But yeah, it sounds like you're very much on the side of, okay, these aren't particularly comparable scale wise. Not only do not know a lot about the way the brain works, but what we do know sort of indicates we're almost there scale wise. So it wouldn't be particularly useful information to know that right now anyway. So okay, it might be possible with today's scale to create an AGI, but it's about the way it's architected and how it's trained that makes the difference. There's an interesting thought here about how many experiments does it take for us to find an architecture which is good enough to be general, because that kind of makes sense to a biological proof point sort of point of view. We know that evolution was able to find at least one architecture that created general intelligence, and presumably, even though it took several million years, it wouldn't have done very many extremely different experiments. It would have been small variation experiments from something which seemed to work a little bit at the start, which, now that I think about it, is kind of where we're at with AGI research in today's world. We have stuff which seems to work a little bit and is intelligent in narrow domains or in very weak cases, and now we're throwing darts around that bullseye at the board, sort of seeing which direction helps. So, I mean, yeah, that's the reason to maybe be optimistic / pessimistic that we could find something that takes us to general intelligence without a complete revolution in the thinking around AGI. Yeah. What do you think about that, Logan?
Well, I mean, I think evolution is very stupid. I love the analogy because it's like, oh, we have an architecture of RNNs and an architecture of transformers. And then like I guess all three of us here are different architectures. I don't know. And then like evolution, like every new genome sequence is a new architecture. Like any mutation is a new like attempt at an architecture. And you also have to like run that architecture on like living however many like minutes or days for flies to like I don't know 60 years or 20 years for humans and whatever environment. And then like for like I don't know automating that, I think you could get there's probably ways of like automating architecture search similar to transformers or other things or and like you don't have to run it for 30 years, you know, but you can run it on like the same data sets and like a diverse range of like 10 data sets and then oh wow it performed really well relative to this other one, so we're going to generate a few offspring off that, and that like is probably super inefficient way of finding an architecture, but like maybe if you have like a really smart way of doing that of like these are the changes that matter or this is a way to figure out the stuff that matters, but I don't know what the field of like architecture search is like doing.
Yeah, because I'm not suggesting copying evolution's way of doing it, which we agree is extremely inefficient. I'm just using it as a example, I guess, to say, well, if evolution had got to a point where it had intelligence as good as our current neural networks on computers, it would be it would spend a lot many more. It would have much more attempts around that space than it would to go a completely different direction to create intelligence with a totally different biological architecture. So we know it didn't try that many different revolutionary ways of doing intelligence. It wouldn't have had many opportunities to. It's sort of following this path of least resistance from something that sort of works at a small scale and gets better and better and better and better. So the fact that we can see it, we don't see that many different, like totally different kinds of intelligence in biology, sort of indicates that the first way that started working at a very small scale was able to scale up with only evolutionary level like changes with only small variations to it before
essentially what you're saying, Hunter, and correct me if I'm misinterpreting, but it's almost like you're saying once you're a little bit close, gradient descent is all you need, you know, because evolution takes these little steps and follows down the slope typically. So you didn't need revolutions after that.
It's a point saying that there probably isn't a giant wall that we can't see ahead of us that'll stop us from getting AI to human level, because there wouldn't have been that many walls when evolution did it, or we wouldn't be able to be here at this early in life.
I think there's one likely, you know, not critique or like counterpoint, and I'm actually curious, Logan, of everyone's thoughts on this, is that could well be true that like you only need gradient descent to find the optimal, but how good is that optimal, right? Like we know language models are good, we know that something around language models can be better, but what's the peak of that? This is back to the ceiling problem of how good can this current paradigm be, assuming, you know, optimization from here onwards without big dramatic changes in the architecture.
What do you think, Logan?
I mean, I do expect different architectures to pop out from like automating ML research. Like you're going to find more sample efficient ways to do that. And alternatively, you find out more efficient training schemes. Like you train in like some 3D environment with different goals or metrics or something like that. But then you could do like architecture search with gradient descent. But I expect you would do like human in the loop to say, like I have a smart idea. Maybe we have to have like current models plus, I don't know, like convolution. At the moment, they do transformers or some things that they're trying to do with convolution neural networks as well. And you do a bunch of algorithms there, and maybe you find one that's sample efficient. And so like the human in the loop putting the good idea is not just stochastic gradient descent. It's like some discontinuous thing from the outside.
So this is where the genetic evolution analogy breaks down, you're saying actually with humans, we can do better than that. We can do bigger hops.
Correct. And if you have like better principles of like architecture search, or you have like the AI generating really good ideas to do as well, because like whatever a human is doing, you can train an AI to automate it at some quality. Then like maybe that is a way. But like I don't know. I'm not too excited about architecture search, even as a way of like scaling capabilities. Like I don't know. It doesn't seem like that's going to be the first thing that causes AGI.
You don't think it's going to be the first thing that causes AGI?
Well, I mean, maybe it's the automating ML research, which then does architecture search.
Which does that.
Like,
so,
yeah. And I'm like, yeah, that's like some probability. Maybe after conditioning on ML research being automated. Like, yeah.
I guess then maybe it is worth kind of just clarifying that, you know, in your view, what is, in your view, like the most probable path to AGI at the moment that you see? You know, I know there's lots of ways that it might not work, like trying to emulate the brain, or you talked about kind of some skepticism about architecture search. So what do you think is the way that it will happen?
The thing I'm most confident in is like maybe in the next few years, I would guess two. Like as said before, some recursive bootstrapping of data or automation happens. People get excited about it. People pay lots of data, or apply some money for data collection, and then ML research gets automated, and then this maybe leads to like neuroscience is going to be different then, and maybe that can be changed or pulled in, or maybe architecture search actually is really cool or very exciting then, or can be very cool if you do it, or maybe it's like very very like data learning schemes plus transfer learning. Like for me, I'm like I don't have a probability distribution between all three of those, and there's maybe a fourth one. Like that seems like I don't have a reason to be confident, but I'm like I am more confident on the automating ML one, which enables the other ones to produce AGI.
Yeah, you can see a couple of doors opening. After that gets a little bit harder, but you can see the steps there where we get to better and better AGI.
Well, I think we're heading towards the end here. So the last thing to touch on before we finish up the episode an hour in is we've spoken a lot about generating AGI, the pathways to it, and when we think it might happen. The final two questions, actually. One is, when is your best guess as to when the first AGI will exist? And then from that point, when artificial intelligence will have more control over our future than human intelligence does? So when do we reach the super intelligence? Look at that. What are your best guesses there?
4 years. So
when do we have 4 years? Yeah, sorry.
For both, or maybe like an extra 6 months.
4 years
that.
For both.
Yeah. Maybe this is the +2. Just add +2.
Yeah. Yeah. For the AGI controlling it, I don't know, because like plus 6 months, it's like I don't know, because like if you don't build the AGI and like do something or ensure some sort of like mutually assured destruction clause between people, then like if you build the AGI and like everyone's crazy and the government doesn't come in and take all your GPUs because they finally realized like someone else is going to build it, I don't know, too, and then there's your opportunity or chance. Though like I really in reality that people like the top AI labs can collaborate with each other, and people in government can like see, or like we're able to like all go towards the same idea of utopia, hopefully with some like lots of moral uncertainty, because like why are my morals right now like actually should be locked in? I don't think they should be locked in. I want to improve and grow, and like I probably don't have the correct moral framework. Yeah.
And we're trying to yeah, definitely get into a lot here, so we might have to take it one step at a time. Logan, just on your first point about timelines, obviously that's a much faster timeline than I think most, and I think there have been surveys on this on expected timelines, and that's faster than most. Do you have a sense of yeah, what would you say to all the people who think the timelines are 4 years feels short? What gives you confidence that it's as short as you just estimated?
Yeah, well, I used to have longer timelines. Then I convinced myself. And so that must mean the change is an improvement. And no, my real reason is I think one convincing thing to other people is like, when do you expect code to be automated? And this is an input to research. And then, like, what about the other parts of research? And like a lot of the things I said in this podcast is you can poke lots of holes into it. And you could also do the reverse of poking holes in the holes. Uh, but like, uh, I intentionally don't go into way specific details on how I personally would automate it because I think I have really good ideas and maybe someone hasn't thought of these ideas. And I would rather them not listen to the podcast and make those 4 years go to like 3.5. Like that would be really bad.
So it's the fact that you can see a reasonable path to get there, even just through the code automation, is convincing you that the timelines can be short.
Yeah, one very interesting thought is that like the shorter timelines you have, um, the more it becomes, the less it becomes forecasting, and the more it becomes, here's how I would build an AGI in 3 steps.
Yeah, and understand that you don't want to share those things for the kind of the risks that it poses potentially, but you in your mind you feel like that's there, that you can see that step one, you see some path where in the next 4 years you can imagine much more capable AGI to the point of general and potentially super intelligence.
Yeah, one thing is I don't have that much expertise, like as expertise as the people working at Google Research, like all these years. And like I've thought of ideas, and I'm like, these seem pretty plausible. And I tell other people's ideas, and they can't poke too many holes in it. And then I'm like, wow, the people at Google could think of much better ideas than me, especially after like with all their research experience, and then also like actually implementing it and that produces more ideas. Uh, so it's just I do think people are way smarter than me in their specialties, and that's like they're gonna once this becomes popular, they're gonna just trump me in ideas and and accelerate ML research.
What is our the very last questions to touch on, which we'll touch on and go in much more depth, is about the alignment and safety stuff. But I just wanted to say really quickly, how would you approach, or what's the best way do you think to approach making sure that whatever models are created in 4 years' time are aligned with human interests in your understanding of the future?
Yeah, my favorite breakdown is that when you reward a model for doing something, this doesn't specify its motivations for doing it, because maybe it was doing it because it wants to, and you reinforce that, or maybe it's doing it because it wants to trick you and gain your trust, and that gets reinforced. And if you, or maybe it's just doing it because it wants to look cool, because all the other like AIs are doing what you want. Like it needs to all have like different out of distribution behavior, especially in like high stakes environments. Maybe it does cause a catastrophe. And so like with like that framing, it's like how do you understand the like maybe not intentions like or like the thoughts, maybe that's anthropomorphizing. It's like there are computations that led to its actions. There's like reasons that it did the thing that it did. It's like understanding what those reasons are, which is like general like interpretability of like at the moment language models. Um, Seems extremely valuable. And then based off this talk, it's like, or like my thoughts, it's like, oh, automating this research also is very, very high value. And how do you do that? And get this in the hands of like alignment researchers, especially when all the best tools are going to be at the top labs. And that's not where all the alignment researchers are.
To find out more, what should we look up to find out more about that approach?
Oh, I don't think we have anything published or like this is our thoughts and takes. One is the Eleuther AI Discord server, and we have the Accelerating Alignment channel, which is pretty dead at the moment because we're all doing different things at different organizations now. But we did scrape an alignment data set, so language models couldn't know that.
Awesome. Well, thanks a lot, Logan. Thank you for coming on board the podcast, and I think that's about a wrap. Thanks everyone for listening, all dozen of you, and we'll be back in a few weeks' time with another interview on AGI timelines, getting the other side of the story, presumably with someone who has much longer timelines than Logan. So we'll have a bit of a dive into that and hear the other points in a few weeks' time. Thank you, everyone.
Thank you so much, Logan. Thank you, Hunter.
Yeah, thanks for having me.